Advancements in air safety are achieved through increased knowledge of aircraft, the people who fly them, and the air through which they fly. Advancements in crash safety are accomplished in a similar manner, by acquiring more knowledge about the behavior of aircraft under crash conditions. In July 1963, a Federal Aviation Agency safety research project was set up. Its purpose? To gain basic knowledge of aircraft behavior under crash conditions through accurate crash load measurements. With this information, improvements can be made in survivability and fires minimized. The first test involved the destruction of a Douglas DC-7 in a crash obstacle course designed to simulate a number of recent actual, marginally survivable crashes. The crash obstacles were of various types. There were barriers to destroy the propellers and landing gear, as in a serious undershoot or overrun accident. There were 2 telephone poles to simulate crash landing in a wooded area. There was a mound of dirt to simulate a wing-low contact with the ground. There was an incline of 8 degrees to create severe fuselage ground contact and strain the capabilities of the aircraft structure and internal experiments. And finally, there was a hill at an impact angle of 20 degrees to subject the structure and experiments to destructive loads. The aircraft was carefully prepared for the tests. We see it here in animation, in a vertical perspective. The right wing, filled with colored water to facilitate study of fuel spray patterns, was instrumented with accelerometers at 7 span-wise locations to measure the longitudinal crash loads. These instruments were also planned to record the decay in crash loads away from the impact point. One tank was filled with gelled water to study its behavior. The left wing, also filled with colored water, had vertically and longitudinally mounted accelerometers to record the crash forces resulting from a distributed type loading. The fuselage, heavily instrumented, contained many tests. In the cockpit were 2 experimental crew seats. To the rear were 2 systems for cargo restraint, as part of a test in association with the Society of Automotive Engineers Industrial Committee on Cargo Restraint. 3 standard DC-7 passenger seats were tested in the forward compartment. A child restraint system was installed, tying it vertically over the seat back and attaching it to the floor structure. The occupant was a 35-pound child doll. Behind these were 2 3-passenger seats typical of current jet transport installations. Adjacent to these seats was an experimental rear-facing seat with energy-absorbing legs. The galley was also prepared, loaded with over 400 pounds of equipment. Aft of the galley was an airbag system designed to cushion passenger impact. The bags were inflated prior to the test. Across the aisle were 2 more standard DC-7 seats. And lastly, there was a side-facing seat test in the passenger lounge. The seats were instrumented for accelerations, leg loads, and belt loads. The aircraft is in takeoff condition at full gross weight, with landing gear down and flaps retracted. The nose wheel has been replaced by a slipper which slides in a single-track guide rail. The aircraft is accelerating to a takeoff speed of 139 knots under its own power. Close scrutiny of this test is possible through the use of many motion picture cameras at different locations, most of them recording the action at 20 times normal camera speed. The velocity of the aircraft at impact is 20 knots faster than anticipated. Here the propellers strike the barriers and produce substantial sparking followed by landing gear separation. The secondary flash is due to flash bulbs used to correlate the electronic data with the photographic data. The high impact speed results in the aircraft continuing over the 20-degree hill and having an added impact on the far side. And here is the action as seen from the front. The initial barriers destroy the propellers. Separate the landing gear. Wrench the engines from their mounts and start engine fires. The pole impact yaws the aircraft. There is a glancing contact with the left wing. The aircraft is pitched up, and the fuselage, weakened by the propeller, fails. There is severe crash impact on the second hill. The fire, which is so impressive in this slow-motion photography, in reality is lasting only through the 5-second crash sequence. It consumes 15 gallons of fuel carried in the right-hand wheel well and most of the engine oil. Actually, there is no fire damage to any part of the aircraft. And here is a detailed view of the right wing. The 12-inch telephone pole cuts off the outer panel, but the heavier inboard section breaks off a larger 13-inch telephone pole. The basic wing structure remains intact. Inside the aircraft, the high-speed camera records the crash effects. In the cockpit, the pilot's seat is a net type, while the co-pilot's seat has an energy-absorbing feature which lets it move forward a limited distance to reduce peak crash loads. The 15 Gs developed downward and forward on the first impact would be survivable. But on the second hill, the nose section is crushed. This condition, combined with 20 G downward and 30 G forward forces, makes this area non-survivable. Both forward cargo restraint systems work well. Neither pallet nor cargo load separate from its original tie-down position. In spite of the initial 15 G downward and 15 G forward impact, as well as the second impact with 20 Gs downward and 30 Gs forward. The DC-7 seats behave as expected under the high crash loads, but fuselage failure at the camera mount location prevents coverage of the entire sequence. And this is a new seat mounted over the wing. It is similar to those recently installed on certain modern jet transports. The crash loads are beyond normal seat design strength, yet the first impact is considered easily survivable. The second, at best, marginal. And this is the new 16G experimental rear-facing triple seat, holding 3 200-pound dummies. It is located over the trailing edge of the wing. At the first impact, the seat reclining locks fail. And this is the second impact. It is likely there would not be survival under these conditions. Here in the aft fuselage, a conventional 6G seat pair holds 2 dummies. A third dummy is strapped in a side-facing lounge seat. The first impact loads, here in the aft section, are similar to those in the cockpit, except that the forward G forces precede the vertical forces. On the second impact, the aft fuselage section just slaps the top of the hill, thus mainly causing downward loads. It is during this second impact that the side-facing dummy's belt attach bolt fails. The forward-facing seats are considered only marginally survivable. Yet, across the aisle, the airbag restraint system retains the dummies in their seats. One is a low-pressure rubberized fabric bag. The other is a clear plastic bag supporting a yellow-suited dummy. The clear plastic bag fails, but the seat belt retains the dummy. While this form of pneumatic support reduces peak crash loads, it creates some serious evacuation problems. An indication of the structural integrity of the passenger cabin is that its aft section has been capped at both ends and is used as a workshop area in preparation for the next crash test. Since these extremely severe crash loads were accurately recorded, the crash test program serves, in part, to spotlight problem areas previously hidden by actual crash damage. A second crash test will subject a Lockheed L-1649 to a modified, less severe crash. This test program, sponsored and supervised by the Federal Aviation Agency, provides a unique opportunity to gain fundamental knowledge of aircraft behavior under crash conditions. These tests will provide a basis for many improvements throughout the aviation community in the United States and overseas. Thus, through continued research and testing by government and private industry, the excellent safety record of our air carriers will be further improved.